This time on Thistle, we're checking out the Trust M cryptographic module from Infineon, and we're going to use this to set up Secure Boot on a BeagleBone Black. So our friends at Infineon make this chip called the Optica Trust M, and it's a really great drop-in solution that lets you add cryptography or secure boot to your existing projects. You can create and store security keys with the latest cryptographic standards, you can generate true random numbers, and you can even protect TLS certificates with the peace of mind that your IOT devices are communicating securely. And the best part is it interfaces over I2C. So if you're working with a constrained microcontroller platform that doesn't have onboard cryptographic features, or if you want to add security to an existing product, all you need is 2 extra wires or an existing I2C bus. So today we're trying out Thistle's new firmware signing feature in the web application, and we're going to keep it simple by just managing the public keys on the Trust M. Now, in the past, we've used the web application for managing over-the-air updates, but once those updates actually hit our target devices, we want to make sure that every time they start up, they're running firmware that's trustworthy and untampered with. So the Trust M module brings that extra layer of security and makes sure that every time our device boots up, it's running the firmware that it's supposed to run.
In this demo, we'll use the Thistle app to generate a key pair and sign an existing firmware image with the private key. Then we'll give the public key to the Trust M and update our bootloader so it can check if the firmware signature matches when booting up. On the BeagleBone, we're using a lightweight bootloader called U-Boot, which supports a secure boot implementation, referred to as verified boot. This isn't enabled by default, so let's take a look at setting this up. All you need is your BeagleBone Black with a power source, a Trust M module with the appropriate wires, and a way to interface with your BeagleBone. In this case, I've got it connected to a local network that I can secure shell into, but you can also use a USB serial adapter to get a console. Up next, you'll have to flash a microSD card with our custom Linux image linked below. To do this, I used Etcher, a simple tool for creating bootable disks, and it only takes 3 steps. Once your SD card is flashed, you can boot from it by holding down the user button closest to the SD card slot while plugging in power, and then release. You can watch the boot up sequence over a serial connection, but if you're using SSH, you'll just have to wait for it to finish booting before logging in with the default credentials. So now let's wire up the Trust M module so we can set up Secure Boot. Referencing this pinout guide, you can hook up the Trust M to the power and default I2C pins on the BeagleBone Black. Back in a console, we'll create a symbolic link between the existing I2C2 interface and I2C1, and you can run sudo trustm_chipinfo to confirm that you've hooked it up successfully. At this point, if you're getting any errors, you might have to give read-write permissions to the I2C ports, and of course, double-check your wiring. Now with our hardware set up, let's talk about Secure Boot. Before an operating system loads on any device, the bootloader is the first process that executes. It's responsible for initializing hardware, fetching configuration files, and of course, loading the operating system or firmware itself into memory. Secure Boot is a process that forestalls attacks at this level, which can be as simple as verifying the digital signature of the loaded firmware, all the way to a multi-step authentication procedure depending on the platform. Now, with a dedicated security chip like the Optica Trust M, we can handle authentication outside of the onboard firmware and boot environment on a trusted piece of silicon. And we can also manage cryptographic key pairs in a trusted space that has its own security mechanisms. With the BeagleBone booted up, let's try manually signing the existing firmware. We'll use the Z-image file, which is a binary of the compiled Linux kernel. Using the secure copy protocol on my laptop, I can copy over the file from /boot/zimage at the BeagleBone's IP address to a folder on my computer. Up next, I can log into my Thistle account in a web browser, and if you don't have an existing project, go ahead and create one, then navigate to Signed Firmware, where you can upload your Z-image file. Give it just a second, and then you can retrieve this zimage.sig file, which is signed with a private key through Thistle's backend. Finally, you can find the public key under Settings and Access. Go ahead and copy that, and next we're going to convert this into a binary format that the Trust M understands. On my computer, I can run cat public.pem, paste my public key, and hit Ctrl-D to create a new file containing my public key. Using the following OpenSSL command, which you can find documented below, we can transform the elliptic curve public key file that we just created into a distinguished encoding rule that then gets converted to hex and then finally outputted to a PK file in binary format, which the Trust M can work with. You can simply copy over that PK file once it's created to the BeagleBone using Secure Copy Protocol. And while you're at it, go ahead and also transfer over the signed image. The last step is to copy over and replace the updated version of U-boot and the corresponding boot script, which tells the bootloader how to interface with our Trust M module, since this requires special pin definitions and communication over I2C. Once you've made it this far, you can use the trustm_data command to copy over the public key to the Trust M. Once it finishes writing, all you have to do is reconnect the Trust M module to pins 66 and 69 on the BeagleBone before rebooting. You can monitor U-boot over a serial connection to get some insight to the verified boot process, and here you can see that the Trust M is detected and reading from the certificate slot that we wrote the public key to, and also we can see that it's able to verify the signature of the current firmware.
If you want to see more projects like this, stay posted on the channel, and I would love to see what kind of applications you guys have for cryptography or the Trust M module in your projects.
Stay up to date with the new features and hardware platforms we're supporting by following us over on LinkedIn and Twitter. And if you have any suggestions, we'd love to hear your feedback, so shoot us a message. I'm Alex Lynd, and thank you for watching Thistle Technologies.